Hi there. My name is Kyle, and we'll be talking about the traveling salesman problem and Christophide's algorithm. So, what is the traveling salesman problem, or the TSP, as I'll refer to it throughout this presentation? Well, the TSP has the goal of finding the shortest path between all vertices or cities in some graph. So, on the example for the right, we want to find, going through all of the vertices here, 1 through 7, we want to find the shortest path to go through all of them that exist. We want to, of course, return back to the very start. So this would create what is called a Hamiltonian circuit, or as we refer to in class, a closed path that returns back to the starting vertex. This only works here for weighted, symmetrical, and connected graphs. Symmetrical in this case meaning the cost to go from vertex I to vertex j is the same as going from vertex j to vertex I. We can see on the right side going from 1 to 2 has a weight of 12, and going from 2 to 1 has a weight or cost of 12 as well. So this is indeed a symmetrical graph. There's some applications of the TSP, such as computer wiring or hole punching, but one that I'm particularly interested in is job sequencing, particularly because this is a computer science based application. And in this case, we have our processors in our computers that have to do a certain amount of jobs in a certain amount of time. And the TSP aims to see what is the minimum amount of time that the processor needs to spend working on these jobs, and what ordering minimizes that time that they will spend working on these jobs based upon how long it will take to complete these jobs. So that the processor does not have to be, stuck on one job for way too long. We're trying to optimize our processor's usage in this case. So let's talk a little bit about complexity for this problem. The TSP, if we're trying to optimize the route through these cities, it is considered what's NP hard. This means that there's no polynomial time algorithm that exists currently in order to solve this problem. Compare this with something that is a non-optimal route, so perhaps some constraints have been relieved on what we are trying to find, and we're not trying to find the most optimized route for the traveling salesman problem. This is considered NP complete. NP for brevity is non-deterministic polynomial time, or there is no polynomial algorithm that exists that can solve these sorts of problems. So NP hard, there exists no polynomial time algorithm. NP complete is like this weird middle ground between NP hard and NP, as we can see on the right side. And it's like easy to verify solutions, but it's difficult to actually find that those what those solutions are, even though we know that they may exist. An example for something that is considered to be P is Kruskal's algorithm, which we will use in just a bit here. This is solved in polynomial time, so it's not non-deterministic, but it is in fact polynomial time. As we saw in class with also Dijkstra's algorithm, that can be solved and has an algorithm that takes place in polynomial time. So what is Christophide's algorithm? Well, it's really straightforward once you start really getting into it. And we'll show an example in just a moment. So we need to start by finding the shortest minimum spanning tree T of the graph. This can be done using Kruskal's algorithms, we'll see in just a bit. We then need to make this minimum weight spanning tree Eulerian. This means that all vertices need to have an even degree, so we need to link all the odd degreed vertices together. This can be completed in O of, or big O of n cubed time, so it's polynomial time. And then once we get this new Eulerian tree or graph, well, yeah, I suppose it would now be a graph instead. We need to apply um, these new edges, and we need to traverse them using what's called shortcuts. Shortcuts are skips that are applied so that we do not traverse the same already visited vertices. Again, we only want to visit them once in order to get a circuit in this case, because the only vertex we can repeat in a circuit would be just the starting and, of course, then our ending vertex. So before we get into an example, let's talk about the 3/2 approximation ratio. So if we consider Z star to be the cost of the best TSP solution for a graph, meaning this is the minimum weight that is possible to get from a given graph, if we were to find a solution for the TSP. Christophied's algorithm for the TSP has a cost of L of t, or the length or cost of the minimum weight spanning tree we would find before becoming Eulerian, so what we receive from Kruskal's algorithm. It has a cost of LM, or the length of adding new edges through the optimal matching, so the operation of selecting all of the odd degree vertices and optimally matching all of them together in order to make an Eulerian graph. So L of t will always be less than or equal to z star, whereas LM will always be less than or equal to z star over 2. Adding them together in order to get the final result that you get from Christophied's algorithm presents us with the 3 halves times z star, or the fact that Christophied's algorithm will always find a Tor, or the Hamiltonian circuit, that is no more than 3 halves times the total cost of the optimal Tor, z star. So this is fairly good for us because this means that um, it will find a relatively sufficient answer, right? And an efficient answer. It's nothing that's going to be too terribly blown out of proportion. It's a fairly low cost solution to the TSP, even though it may not always be um, the best. It is not always going to be equal to Z star, but it's relatively close. So let's look through a work example here. So we have 5 different vertices, A through E, with very small edge weights, just for the sake of an example here. So for Kruskal's algorithm, we're going to order all the edge weights from lowest to highest. So we'll start with the edge weights of 1. We'll go ahead and add this to the graph. We check, does it create a cycle? If not, we should be good. We're going to include these vertices now. We'll go to the next edge that has a weight of 1. We're going to check, is there a cycle? There's not, so we add this vertex in. Then we'll start with the edge weights of 2 since we finished all the edge weights of 1. We'll check this one here. Does it create a cycle? It does not, so we'll add it and its vertex to the minimum weight spanning tree. We do not include the edge from B to D because if we check it, it does create a cycle between B, E, D, and back to B, so we cannot include that in the minimum weight spanning tree. We then go to the edge between B and C, which is an edge weight of 3 since we've exhausted all the edge weights of 2. And now we check, is this creating a cycle? If not, we're good to add it to the minimum weight spanning tree. And we have found all the vertices, so we stop here. So this here is now our minimum weight spanning tree. So we've completed step 1 of Christophied's algorithm. Now we'll move on to step 2 and make it Eulerian. We see that there are 4 distinct vertices that are not Eulerian, or that make this not Eulerian. So we need to find a way to be able to connect them optimally. We could connect C and D with the edge weight that was previously there of 5, and we can connect B and A with the edge weight of 2 going forward and backward. So now all vertices have even degree. So E has a degree of 2, A is a degree of 2, B a degree of 4, C a degree of 2, and D a degree of 2. And this would be the ending result of Christophied's algorithm, and this would produce an Eulerian graph that would help us be able to solve the traveling salesperson problem efficiently. Thank you.